So, let us continue in this lecture for the cylindrical wave functions, and in this part we are going to see how the appropriate choice of the magnetic vector potential and the electric vector potential in terms of the z directed psi function or the substitutions A equal to uz psi leads to the Tm to z mode in the cylindrical coordinate system, and what are the field distributions for those modes, and how the substitution F equal to uz psi leads to the T to Z modes, and what is the field distribution, the electric and magnetic field distributions, the mathematical expressions for such fields. This is going to directly lead to the solution of the circular waveguide, where we will find that the modes inside the circular waveguide are indeed the TE to Z and the TM to Z types, because of the very simple reason that those fields which we are going to find now they are going to satisfy the boundary conditions at the conducting walls of the circular waveguide. So, therefore, conceptually the treatment is not different from the rectangular waveguide, it is only the mathematical language that changes. Okay. So, the whole cylindrical coordinates circular waveguide system proceeds in exactly the same way, except the difference in the mathematical language. So, we are just now going to start our exploration of what are the fields for A equal to uz psi and F equal to uz psi. Let us go to the lecture. So, let us suppose that first of all that A equal to uz psi. We call this equation 18. We know that H is equal to curl of A, and curl of A in the cylindrical coordinate system is 1 by H1, H2, H3 determinant of H1 AU, H2 AV, H3 AW, del del U, del del V, del del W, H1 AU, H2 AV and H3 AW. So, therefore, H given by curl of A becomes 1 by rho, substituting for H1, H2, H3 as we did before. A rho, substituting for U V W, rho A phi, A z, A z, del del rho, del del phi, del del z and 0 0 psi, because psi has only a z component, not new to us. Similar treatment we had done in the rectangular coordinate system, and this is equal to 1 by rho A rho del psi del phi minus 0 plus rho A phi 0 minus del psi del rho plus A z 0 minus 0. So, that becomes A rho 1 by rho del psi del phi minus A phi del psi del rho. So, H rho is given by 1 by rho del psi del phi, H phi is given by minus del psi del rho, and H z is given by 0. That we can easily deduce from the above equation. So, we call this equation or sets of equation for the magnetic fields equation number 19. Similarly, for the electric field, we encountered this equation in the rectangular coordinate system, minus j omega mu a plus 1 by j omega epsilon divergence of grad A. And now we are going to express the same thing in the cylindrical wave system or the cylindrical coordinate system. So, we call this equation 20. So, now divergence A in the cylindrical coordinate is 1 by h1, h2, h3 del u, h2, h3 au plus del v, h3, h1 av plus del w, h1, h2 aw. That is equal to 1 by rho del rho of rho a rho, just substituting for h1, h2, h3 and uvw plus del phi a phi plus del z rho a z. That is equal to del phi del z. That is equal to del psi del z, as A has only a z component. Now, grad of V in the cylindrical coordinate system is, where V is the scalar, is given by 1 by h1 del V del u au plus 1 by h2 del V del V. Note that this is a capital V, this is a small v, a small v plus 1 by h3 del V del w aw. So, that is equal to del V del u arrow, substituting for u, v and w, plus 1 by rho, substituting for h1, h2, h3, 1 by rho del v del w, sorry, del v del phi a phi plus del v del z plus del V del Z is it. And grad of divergence A can therefore be written as grad of del psi del Z, because we already found that divergence of A is del psi del Z, and that is equal to grad square psi del rho del Z A rho plus 1 by rho grad square psi by del phi del Z A phi plus grad square psi grad del plus del square psi del Z square is it. So, this is equal to del square psi del rho del Z A rho plus 1 by rho del square psi del phi del Z A phi put it here A phi plus del square psi del Z square is it. So, just substituting from the previously derived the previous expression for grad of V, where V is a scalar. So, now from equation 20 we can write the electric field as minus j omega mu psi Z plus 1 by j omega epsilon del square psi del rho del Z times A rho plus 1 by rho del square psi del phi del Z A phi plus del square psi del Z square is it. So, that can be written as A rho 1 by j omega epsilon del square psi del rho del Z plus A phi 1 by j omega epsilon rho del square psi del phi del Z plus A Z 1 by j omega epsilon del square del Z square plus k square psi, where k square is given by omega square mu epsilon, which is well known. Therefore, we can collect together the terms for the electric field from this expression. So, E rho will be equal to 1 by j omega epsilon del square psi by del rho del z. E phi will be 1 by j omega epsilon rho del square psi del phi del z, and E z will be equal to 1 by j omega epsilon del square del z square plus k square psi. So, these constitute the electric fields for the TM2Z mode. Why is the mode TM2Z now? Because back from equation number I should say so why are the fields TM2Z? Because back from equation number 19 we see that the Z directed magnetic field is 0. So, the mode is TM2Z. So, similar to the rectangular waveguide or so similar to the rectangular coordinate system, Z directed magnetic vector potential will give rise to the TM2Z mode in the cylindrical coordinate system as well. So, let us explore now what will happen for the Z directed electric vector potential, whether it gives rise to the TE2Z mode as it does for the rectangular coordinate system. So, for the TE2Z, let F equal to uz psi. So, E is given by minus curl of F, and that is given by minus 1 by rho a rho rho a phi a z del rho del phi del z and 0 psi, and that ultimately yields minus 1 by rho del psi del phi a rho plus del psi del rho a phi. So, therefore, E rho is given by minus 1 by rho del psi del phi, E phi is given by del psi del rho, and E z is given by 0. So, we clearly see from here itself that the mode is TE, because the Ez, the Z component of the electric field is 0. Call this equation number 22. Then we go ahead with the magnetic field. H is equal to minus j omega epsilon F plus 1 by j omega mu grad of divergence F, call this 23, divergence F divergence f is given by 1 by rho del rho of rho f u plus del phi of f phi and plus del z of rho f z. And because f has only a z component, this boils down to del psi del z. Now, grad of divergence f becomes grad of del psi del z, that is equal to del square psi del rho del z a rho plus 1 by rho del square psi del phi del z a phi plus del square psi del z square a z. So, now from 23 we can compute H as minus j omega epsilon a z psi plus 1 by j omega mu del square psi del rho del z a rho plus 1 by rho del square psi del phi del z a phi plus del square psi del z square a z. That is 1 by j omega mu del square psi del rho del z a rho plus 1 by j omega mu rho del square psi del phi del z a phi plus 1 by j omega mu del square del z square plus k square psi a z. So, from here we can find out all the magnetic field components, which is H rho equal to 1 by j omega mu del square psi del rho del z, H phi is 1 by j omega mu rho del square psi del phi del z, and H z as 1 by j omega mu del square del z square plus k square psi. So, these are the 3 magnetic field components in the cylindrical wave system or the cylindrical coordinate system for f is equal to u z psi. Let us call this equation 24. and an arbitrary field, one which have both a Ez and an Hz, can be expressed as a superimposition of the T to Z and the Tm to Z fields, just like in the rectangular coordinate system. So, any arbitrary field can be expressed as a summation over T to Z and Tm to Z fields. Okay. So, this completes the derivation of the T to Z and the Tm to Z electric and magnetic fields in the cylindrical coordinate system, and the simple conclusion is that A equal to uz psi leads to the Tm to Z modes as in the rectangular waveguide, and the substitution F equal to uz psi gives rise to or yields the T to Z modes also similar to the rectangular coordinate system. So, let us stop here.